This is a computational model for basically taking engineering for chemical reactions and basically adding a nucleostatic axis for those. And basically what you can do is engineer where every electron moves in a chemical process. Now, the object here is that today, the current system, and the challenge is that the modeling uses machine learning. It basically figures out where the electron distributions are and sort of guesses how to get there without a clear process from chaos to settled structures. It's sort of working backwards. My solution uses a hemispherical frame of reference, that is radial, inclination, longitude, latitude for phi, and z for which hemisphere, replacing quantum numbers and also determining the interdimensional stress and the doubling of these things in these abstract equations that we already use. That means there's only one electron distribution and all the rest of them flow from that by the natural pattern of settling. Now, we all know that densities have longitudinal rings. This is our textbook over here. You can see all these things. I focus on Bose cylinders. That is that the structure is for a multi-electron set, a cylinder with 2x for 2 in each hemisphere. Now, this is the distribution that I'm going to end up with, okay? Again, it's got hemispheres, but it also has that electron gets pulled by weak force towards the axis, but 1/2 of that linear momentum translates into a rotation energy, and that's important when we get to electroweak later. Also, notice that there's a point out here at the equator where, even though these are deep energy wells, there is a little node out here, by the way, we'll do these calculations. So what happens? Once you fill that, this electrostatic is much stronger, and so the next ones have to find the same distance and the same angle, so the same energy, and so we get longitudinal rings. Relative, after that, subshell-s fills that position. Okay, now let's talk about this Bose cylinder and making it real 3D engineering. Okay, so I'm saying that there's 2 equilibriums, radial, proton, electron, electrostatic, clearly, we all know that. There's also this extra 1/r, which is called angular momentum, but I actually will think it's closely related to tau and omega and the hypercharge that we apply within the nucleus, but applied at these remote distances. Further, in this axial direction, we have the weak force, the third fundamental force, offset by multiple electrons that repel each other. So there's collisions, which is the typical of the Schrodinger equation. Now, this is the same thing said this way. Don't have time for it. Okay, in that axial plane, obviously you have the green inward, that's the weak force, okay? And you have the aggregation of these vectors, which becomes directly outward, and so there is an equilibrium position that creates this cylinder surface. And instead of it being orbit, as Bohr said, it becomes collisions along this arc, okay? And interestingly enough, what happens though is that if you have these circles, they want to offset by 1/2 phase, which means that the poly pair is at exactly the 180-degree position, and these are slightly tighter by that. The opposite hemisphere and a second layer at the same count, so you get the 2888, fits because of the 2 hemisphere system, okay? Now, let's see what those forces look like as vectors, okay? Obviously inward, outward, and towards the pole, but remember, the full amount of it, only 1/2 goes here, and 1/2 of it goes into rotation. This makes for some of the strange behavior of subatomic particles. In fact, I'm going to relate that directly to existing equations that we have for electroweak, because these we don't apply any angles to, but for electroweak, we do. We apply the Weiberg angle, and I'm relating that to a physical angle, which is between particle 2, particle 1, and the axis of particle 1, Z0. So as a result, I now have 3 equations or 3 densities or 3 things which I can do. So obviously we have radial electrostatic, proton electron, that's easy enough. We all know Coulomb, although I prefer my version, which includes the Planck constant, the speed of light. And then I use the scaling ratio of the particle edge, which is the maximum strength, to the Bohr radius, which is the equilibrium between all these systems, because that's the scale at which all of these 1 over n to the x exponents apply. Obviously, that gives us a radial only direction, so now I can start to apply functions and density functions in this radial direction. And this is true for all electrons, but as a separate segment, I'm going to have 3 equations for the electron nucleus and only 1 electrostatic between the electrons. Okay, now the equation 2 is this extra 1 over r, by whatever name you want to call it. And all I do is I add this. So it will balance at the Bohr radius because I'm doing 1 over the distance, and that comes to 0. The rest of it is the same. But because it's 1 over extra r, at the field level, when you do DFT, that 1 over distance cubed from the volume it does, when you integrate over that extra axis, it becomes a quarter. So you have to translate 4/3 to get the equations to work as if electrostatic. And this is very important to understanding those strange counts and masses of elementary particles. So you get this electroweak that actually has the real portion and this offset portion. Okay, so the cosines is the portion that we're going to define. So as a result, I basically say that this equation, which is a true conservation of energy, is slightly misstated because that's a linear. But in part, if you can make this as the rotational transfer, you can basically repulse it. And so you have a linear plus rotational, and the energy goes into this invisible rotation of this density. Okay? Further, it must satisfy Dirac's 4th equation. We do a lot with electroweak, but we forget about Dirac. Okay? No, his number 9 is this strange quantum challenge of 1/2 there. And that's the mu, is the magnetics. So that becomes the rotation. And it is only half of the standard function. So as a result, we've got to satisfy Dirac, we've got to satisfy electroweak, but that tangent is really cosine, sine over cosine, which means that I can use this equation ultimately, and I have no discontinuities, and I will satisfy both equations. As a result, I get the axial direction as this sine cosine, obviously that existing hypercharge equation that I did, or angular momentum extra 1 over r, but I have to split it between radial and theta because of its directions, okay? And then further in the z direction, I will be transferring energy to this rotational, so this extra 1 over r makes sense. The T3 that's in your equation actually becomes a invisible rotation, and that becomes in your exchange coefficient difference on the x0 as a rho to the cube root, again, because of the exponents, that extra 1 over r. So as a result, we have radial electrostatic pulling electrons in, extra 1 over r pushing them out, the weaks from 0 to 90 degrees, basically having this, but at every point there is this theta direction pulling it towards the things. That's what gets you this distribution. So what does the model do? Basically, obviously, it's simply, hydrogen all by itself, it nice bounces around and settles around the Bohr radius, okay? In the helium model, the 2 electrons go to the ends, okay, to the opposite ends. There's no real angular because they get pulled to the poles, okay? Much more interesting, though, is CH4. So CH4, this electron, bounces around a little bit, but eventually settles down around 69.5. And that is the 109.5 that we know from experimental evidence. Even more interesting is I do boron fluoride with a self-setting process. 1 electron goes to the Z. This is along the axis direction chosen. The second electron goes here, but the 3 electrons want to stay at the equator. They'll stay there for millions of cycles. Obviously, they're not in exact positions because they bounce off of each other, but generally, you have an equatorial ring of 3, which becomes the tri-planar bonding that experimental evidence shows. Finally, and I think most interesting, when I do this model, basically subshell D and subshell F are interlaced, so they're slightly closer at the off axis, and the along the axis line up. So the subshell-s distance is greater. So subshell D and F fill with N, but have the energies of N-1 and N-2 respectively. That's something that no other computational model can do in a natural settling process. Now, obviously, I got much more work. I got to do more elements, more molecules, and then clusters. And then I need a settling process, which in order to do this, I'm going to have to add duopoles. That's two locked at 100 degrees Dirac monopoles. Instead of doing it at AO, I'm talking about what happens at the R sub E, the particle edge, because you still have two poles there for this hemispherical system. We've got the transfers. This weak force then has to get integrated into magnetism, and the stress then on that hemispherical system becomes photon generation. Thank you.